Have you ever wondered how a tightrope walker can stay so perfectly still, way up high? Or how a giant skyscraper manages to stand tall against crazy winds? You know, it really seems like magic, but it's not. It's actually a basic principle of physics. And today, we're going to pull back the curtain on that secret. So let's dive in. I mean, think about something simple, like a ruler. How is it even possible to get it to balance on just one tiny point, like the tip of your finger? It feels like it should just fall right over, but it doesn't. It just holds steady. So what's the hidden trick here? Well, the secret to the whole thing lies in a single invisible point that exists inside every single object. I'm talking everything from the pencil on your desk to the tallest building in the world. This one point is the absolute key. If you understand this, you understand the secret of stability itself. So what is this magic point really? While it might feel like magic, I promise you it is pure, unadulterated physics. Let's get into what scientists actually call this thing and what it really means. Okay, so officially, this point is called the center of gravity, or CG for short. The easiest way to think about it is as the average location of all of an object's weight. It's like if you could squish down all the mass of an object into one single tiny spot, the CG is where that spot would be. It is the perfect balance point. Now, this quote gets right to the physics of it. And okay, the algebraic sum of the moments of weights is zero sounds super technical, I get it. But all it's really saying is that at the center of gravity, all the little twisting and turning forces that are caused by gravity, they all perfectly cancel each other out. That's why the ruler balances. At that exact point, there's no leftover force trying to pull it down one way or the other.
All right, so this point is clearly a big deal, and it turns out it follows a few simple but really, really powerful rules. And once you know these rules, you can start to see them everywhere and even predict how things are going to behave.
So there are three main things you gotta remember. First, where the CG is located depends entirely on how an object's mass is spread out. You change the shape, you change the CG. Second, and this is where it gets kind of mind-bending, the CG can actually be outside of the physical object itself, just hanging out in empty space. We'll look at that in just a sec. And third, and this is a big one, a lower center of gravity means a more stable object. That's a huge deal in pretty much all of engineering. And here is a perfect example of that second rule. For a solid disk, the center of gravity is exactly where you'd guess it would be, right smack in the middle. But now look at the hollow ring. Its center of gravity is also in the geometric center, which means it's floating in the empty hole in the middle. The ring is literally balancing around a point of nothing. How cool is that? Okay, now for the fun parts. Knowing what the center of gravity is, that's one thing. But how do we actually find it? Well, for some objects, it's actually way simpler than you might think. For regular symmetrical shapes, geometry has our back. For a rod or a square, it's right where you'd expect, dead center. For something like a triangle, it's at a special point called the centroid. These are really useful to know because, well, these simple shapes are everywhere. But let's be real, most things in the world aren't perfect squares or circles. What about something with a totally weird, irregular shape, like a random piece of cardboard or a rock? How in the world could you find its center of gravity? Well, it turns out there's a really simple and kind of brilliant trick for that. It's called the plumb line method. All you do is hang the object from a point near its edge, and then you let a weighted string, that's a plumb line, hang straight down over it. Gravity guarantees the CG is somewhere on that line, so you trace the line. Then you just hang the object from a different spot and do it again, and where those lines cross, boom, that's it. That's your center of gravity. It's so simple, but it works every single time. Remember that first rule we talked about? How mass distribution matters? Here it is, in action. You've got two cones, same height. The solid cone's center of gravity is pretty low at just 1/4 of its height, because its weight is spread all the way through. But the hollow cone? Its mass is all on the outside, which actually raises its center of gravity to 1/3 of its height. That small difference means the solid cone is naturally going to be way more stable. So we know what it is, we know how to find it, but why should you even care about this invisible little point? Well, because out here in the real world, its position is literally the difference between something standing strong and it falling flat on its face. The center of gravity isn't just some abstract idea you learn about in a physics class. It is the absolute #1 key to an object's stability. Everything, from the design of a supercar to how a toddler learns to stand up and walk, is all about managing the center of gravity. Let's go all the way back to our ruler. If you have a 100 centimeter ruler, Where does it balance? Right at the 50-centimeter mark. And why? Because that's its center of gravity. If you try to balance it anywhere else, like at 40 centimeters, the weight that's acting down at the 50-centimeter mark creates a turning force and, whoops, it topples right over. The balance point is the center of gravity. And all of this leads us to one of the most important rules in all of design and engineering. If you want to make something really, really stable, you have to get its center of gravity as low as possible. That's why race cars are built so low to the ground. It's why ships are loaded with the heaviest cargo at the very bottom. It's all about dropping that CG. So there you have it. The whole secret of balance just boils down to that one single point. And we've learned that a low center of gravity is the key to making something stable. But that gets me thinking about a really interesting question. What things out there are actually designed to be unstable on purpose? If you start looking around, you might be really surprised by what you find.